Hi, in this video, we'll go over the most commonly used computer vision library out there called OpenCV. So this will be a fast crash course with the OpenCV library. I'll show you exactly how you can do things like image manipulation, morphological operations, face detection, edge detection, and a lot more. Yes, you will learn to do all this with OpenCV and Python. And this video is not part of the computer vision for everyone episodes. So this will be unscripted. So be prepared for a lot of mispronounced words, awkward pauses, and ums and ahs and all that. And let's get started. So for this video, I will be going over this notebook, this Jupyter notebook. So this notebook contains a lot of basic operations on OpenCV. So it's not everything in OpenCV obviously, but like it's a lot, it's still a lot. And for the most part, you will be needing these functions in almost any application that you can think of in which you want to use OpenCV. Once you know how to use these operations, the rest of the stuff will just come to you. All right. So this notebook is part of a blog post which I've written almost a year ago. So the video I'm making right now is video version of this post. So this was a crash course in OpenCV in which I went over all the basic operations and functions in OpenCV that a person needs. So if you just want to read the written version of this tutorial, you can head over to this blog post. The link would be in the description. And this Jupyter notebook, along with a collab version, a Google Colab version of this notebook, you can download these notebooks when you hit the download code button on this blog post. So all the code can be downloaded once you head over to this blog post and just, download the source code. So now let's discuss the prerequisites for this video. So the prerequisite is that you need to know how to program in Python. You need to have a basic understanding of Python. You don't need to know OpenCV because I'm going to teach you that right now. But you do need to understand how to program in Python. You should also have Python interpreter installed, or maybe Anaconda package manager which comes with a Jupyter notebook. So I'm going to be using a notebook, but if you use PyCharm or something like that, you can still follow along, but I will be providing you the notebook. I'm not going to provide you a script, Python script which you can just import in PyCharm or something like that. You can still use that notebook. You can copy paste code in an ID, but I would highly recommend that you follow along with this video by using that Jupyter notebook which I'm going to provide to you. So again, a local version of this notebook which I'm using right now, there is an online version, a Google Colab version. If you don't know what Google Colab is, you can just go to Google Colab and then you can click on this link and you will be presented with this notebook. So if you have no idea what online notebooks are and what Collaboratory is, then this is an introductory notebook which teaches you like what Google Colab is and things like that, how you can run the cells and all the basics. And in fact, you can even Google it. I think most of the people that are in the AI and data science space are familiar with Jupyter notebooks and stuff like that. So I'm not gonna cover in depth how how a Jupyter notebook functions and stuff like that, because I'm assuming a lot of people would be familiar with it. Even in fact, you're not, you can just check out this basic Welcome to Collaboratory notebook and Google a few videos and you'll all set to go. All right. So we've discussed the prerequisites. I was also discussed that I have an online version, so you don't need to install anything. And so now let's talk about OpenCV. OpenCV is the biggest computer vision library out there. It contains like 2,500 optimized algorithms in computer vision. And these algorithms ranges from a variety of tasks. I mean, you can do action recognition, extracting 3D models. Yeah, I have a list right there. So these are just a few things that you can do with OpenCV. Almost any computer vision task that you can think of, there is a module for that in OpenCV. So it's a vast library, and I don't think there is any other that even come close to OpenCV. So it's a must learn for any computer vision practitioner out there. In fact, I'm going to make another video just on OpenCV, and its historic background and resources, and what's the advantages by using the C++ version and the Python version, why would you install it, and the source installation versus the pip installation, and a lot of stuff like that, and what are the best resources to learn OpenCV, stuff like that. So I'm going to make a separate video on that, because there's a lot of things that I know I can teach you guys in this particular space, because I've been working with the official OpenCV team for quite some time, and I can provide some great insights on how to actually learn OpenCV, and what are different cons and pros and different things in OpenCV. All right, so a separate video, I'll make a separate video on that. For now, let's just jump right into the installation part. So all you need to do is just open up the command prompt and just type pip install OpenCV contrib Python. So that's just like launch up the command prompt and do pip install OpenCV and contrib Python. Okay, so once you hit enter, the OpenCV package would be installed. Obviously you would need Python interpreter installed, because pip would then not work. So there's that. So one or two things which I would discuss right here is, there are two ways that you can go about the installation. One is that pip install OpenCV contrib Python, and the other one is pip install OpenCV Python. And the difference between the two is, when you do the pip install OpenCV contrib Python, you're also installing a contribution package. It's a separate module which comes along with, it's a small package which contains a series of modules, and it's each module is a contribution by some person, some developer, which has contributed some algorithm to the OpenCV. So when you do that, you're installing some extra bunch of algorithms along with the default OpenCV package. So you're getting more than just OpenCV when you do pip install OpenCV contrib Python. So, but when you do pip install OpenCV Python, you're just getting the OpenCV still, which is still, contains a lot of algorithms. But I would strongly recommend that you do this, because in the contrib package there are one or two interesting algorithms that I frequently use, and I find it pretty useful. Along with OpenCV, you will also need to install NumPy. If you've installed Anaconda, and it would have installed NumPy by default, because it's a numerical computation library which is used for data science tasks a lot. So you just need to install this OpenCV contrib Python, and then you need to install the NumPy package. So these two packages are just required. I also use matplotlib a lot, so if you could also install that library. But for this tutorial, I'm not going to be using that. I'm just going to use the cv2.imshow function in OpenCV, which is used to display the images. But moving forwards, I mostly use matplotlib because it works well with Google Colab. Right. Oh yeah, so I should also tell you, one con of using Google Colab is that if you're using Google Colab instead of running this locally in your PC, one con is that you won't be able to use the GUI functionalities. So the camera, you can't just process a live recording, or you can record a video, then once you record it, you can process it and display it and something like that, but you won't be able to process live feeds, and you won't be able to also pop up windows, meaning a popular OpenCV function is cv2.imshow function, which I'm gonna go about in a minute. But you won't be able to use any GUI functionalities, you won't be able to access your camera live. Although there are many workarounds, like you can use your camera to take a snapshot, then pre-process the image. So there are things around that. Maybe I'll make a separate video on how to use these hacks in Colab. But in essence, if you want to use your camera live and GUI functionalities, then you need to be running this notebook locally. All right. By the way, the Colab version, if you're using a Colab version right now for this video, it's totally fine. I mean, you will get 100% out of this tutorial from this video, even if you're using that. Once you have installed OpenCV in your system, you need to now learn how to read some basic images with OpenCV. Once you read an image, you will then be able to pre-process it and apply various algorithms to it. So To use OpenCV, what you first need to do is do import CV2. CV2 is the namespace for the OpenCV library. Once you do that, you will be able to use OpenCV functions inside the notebook. I'm also importing the NumPy library like this, import NumPy as NP. Now that I have imported these two libraries, what I need to do to read images is use this function, cv2.imread, and then I will pass in the path of the image. So the image is present in this media folder and the file name is 2.png. So this is the path and the name of the image. So that's the first parameter, and the second parameter or the argument is how I'm gonna read this image. So there are a number of ways which you can use to read the image. Let me show you. So here's what you would do. You would head over to the OpenCV docs, which is this URL, docs.opencv.org, the version number and this URL. I'll include this URL in the description of this video. I'll also touch upon some of the documentation here when I'm going over this notebook, and I'll discuss some really interesting things and regarding and touch upon some important concepts. But right now what I'm going to teach you is how to figure out by yourself any argument or number of arguments available for any OpenCV function. So I'm just going to teach you about I'm going to teach you about how to figure out what this argument, what arguments are available for the imread function, but the same concept would generalize to any OpenCV function. So once I show you this, you don't need me to tell you what a particular argument in some particular OpenCV function means. So what you need to do is head over to the OpenCV docs. Now change the version number to the version number which you installed. So right now I know that I installed 4.5.1. How did I know that? So if you went to PyPy, where the PyPy is the package installer which we used, pip install OpenCV content Python. So this is where we installed the OpenCV library. So on PyPy the latest version is 4.5.1. And so I would note this version, and then I would make sure that from here I am selecting the latest version. So after doing that, what I would do is head over to this search bar and type in the OpenCV function which I'm interested in. I'm interested in the imread function. So once I do that, you don't need to put cv2.imread. Just put the direct function's name, imread. So I'm going to click on that URL that popped up, and this is what I'm going to see. So this is the C++ syntax, and this is the Python function, cv2.imread. Right now just is cv because the person who imported, well, people used to do like this. I mean, import cv2 as cv. So OpenCV is documentation is filled with imports like that. So that's why you would see cv instead of cv2. All right, so heading back to that documentation, you would see this retval cv.imread file name, which is what I've just showed you, and the flags. This is the flag which I'm using right now, 0. So what options do we have available on flags, and what does each option do, right? So what you would see here is these are the number of formats that are available as an image that you can use. So you can see you can use a variety of image formats in OpenCV. But what we're really interested in is that we need to scroll down a bit, and we're looking at parameters. So these are the file names, name of the file to be loaded, and this is the flag. This is what we're interested in. So it says flag that can take value CV imread modes. So we need to click on this imread modes. So now we would see a bunch of flags available to us. So you can see all these flags are something that you can use in that function, and each flag is also associated with a particular number. So for example, the grayscale version which I'm using, it's associated with the number 0. You can either use the full names of the flag, or you can use integer number which each flag is assigned to. So for example, I can, instead of using 0, I can do something like cv2.imread, like a grayscale, and it would still work, right? So there's that. So what 0 does is the number 0 is basically assigned to this mode, imread grayscale. It means the image would be loaded in the grayscale mode. The grayscale is just a black and white mode. And I'm gonna exactly show you what the grayscale image looks like. But before that, let me just, like print out the image. And once you see that image by yourself, you would understand, like how the image was read. All right. Now that I've read the image by using cv2.imread in grayscale mode, or maybe the black and white mode, which is the second name for it. So the image is now stored in this variable img. And now I'm going to print out this variable. So as you can see, this is the image which I'm getting right now. Now, I'm not going to tell you what this image is or what this image looks like, but I can guarantee that many of you can figure out what's written in this image by just looking at this. And you can even tell a lot more about this image. For example, you can tell this image is a plain image which has written a number 2 in it, right? And in fact, you can even tell get more specific than this. You can tell that this image is a black image because you're seeing a bunch of zeros here. And I'm going to tell you in a bit what zeros and 255 over each number represent. But for now, you can see that the background is a singular color because it's a singular number, right? And 2 is written also on a singular number. So if 0 is supposedly black, then the 255 would mean white, right? So it's a black image with 2 written on it. So, and what's the size of the image? If I ask you, what would you tell me? So I'll give you a second to figure out what's the size of the image, and then I would show you. All right. So to check out the shape of the image or the size of the image, I would just do img.shape. So it's telling me 21 by 22, and it's rows and columns, or X or Y or whatever width or height you want to call it. So you can also confirm this width or height of this image by counting the number of rows and the number of columns of this image.
Alright, let's just briefly look at how grayscale images are represented in OpenCV. We just learned to read an image and print it out, right? So in OpenCV, the images are represented as a set of pixels, and each pixel has a value from the range of 0 to 255. And this is how it looks like. So we have 0, which represents black, and then 255, which represents white. And all the numbers in between are different shades of gray, right? So this is how a black and white or a grayscale image looks like. It's the same image format which we used to have in the 1950s before, we had color channels and stuff like that. So this is how the grayscale images work in OpenCV. A lot of functions in OpenCV require grayscale images nowadays. So what we do is either we load images in grayscale, or we use a color conversion function to convert color images into grayscale, right? So this is how we work with grayscale images in OpenCV. Now let's look at how color images are represented. So we know if we need to represent an image in a singular channel grayscale, we just need a singular matrix, right? One image matrix. But when we have color, so we have 3 different image matrices, or 3 different channels of images, and each channel represents primary color channel, red, green, and blue. In OpenCV, instead of RGB, the images are represented as BGR. So the blue comes first, then the green channel, and then the red channel. So if we look at further in these channels, we would find that these are 3 different matrices. So we have 3 BGR channels, then there's the height, and then there's the width. So we have 3 dimensions, right? A channel dimension, a height dimension, and a width dimension. So we just saw how images are represented in OpenCV in terms of matrices, how a grayscale image is represented and how color image is represented. So the 0 here stands for grayscale images, right? So when I change this 0 to 1, now the image 2 would be loaded in color. Now, although the image itself is not colored, so what OpenCV would do, it would just duplicate the channels times 3, so it would be a color image. So when I print this out, I would get this. So what is this? So because I just loaded the image in color. So previously the full matrix would be multiplied by 3, and then I would have this long big matrix. And since the print function just doesn't display these big matrices, so it just have cut it out the parts here, which you can see that by the 3 dots here. So it has cut out from here, 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 and here. So right now what I'm trying to tell you is that printing is not the right way to check out images. What you need to do is read an image and display it like it's an actual image, right? Display it properly. So we have a function for that in OpenCV. But before that, I just need to cover the 3 foundational ways, or the 3 main ways you can load images in OpenCV. One is the grayscale mode and the other is color. The grayscale is 0, the one is color, and then there is the third one, which is you load the image in its original unchanged format. Meaning the way the image has exists in the disk, you load it as it is. So if it's color, the image will be loaded as color. If it's grayscale, the image is loaded as grayscale. So if we already have a function flag for loading specifically in grayscale or color, why do we need this third -1 function, which is short by -1, indicated by -1, right? So we need this when we're working with transparent images. Before I show you what transparent images are, let me show you the flags here. So the flags, so yeah, these are the flags. This is the flag which I'm talking about. ImRead unchanged. So this is format in which you can load images, transparent images. So transparent images are also called images with an alpha channel. This is the 4th channel. So in grayscale images, you have a single channel, the image intensity channel with its height and width. In color images, you have 3 channels, the red channel, the blue channel, and the green channel. But in transparent images, there is this 4th channel called the alpha channel, which is a 0 to 255 mask, which tells you what part of the image will be displayed and what part would be hidden and replaced by the existing background. So before I tell you what transparent images look like, I'll show you, I'll Google it and then show it to you. But before that, just I'll tell you how I'm figuring out the numbers here, 0, 1, 2, 3, because I don't see, like these numbers mentioned here. So what you need to do is just copy this immediate unchanged and then go here, put CV2 and then ImRead and then unchanged. All right, so once you run that, you would see that this prints out -1. So this way I know for each flag what equivalent integer number is. So that's why I just don't type the whole flag. I just type its equivalent integer value. So for if I put this grayscale, it would give me 1. So this way I know if I need to load an image in grayscale, I would just put in 0 and I would get a grayscale. So this is how I'm figuring it out, how each number represents what. All right, now let's take a look at what transparent images actually look like. So what you need to do is Google logo, right? I'll just show you what a Google logo looks like, and I'll go into images, and then if I click on there, when you see this checker pattern, this checker pattern tells you that this image is a transparent image. So if I look at this, there's no checker pattern here. So this isn't a transparent image. But when I download this image, it would be a transparent image, meaning the only visible parts would be this, and this checker pattern would be replaced by the background that I put this image on. So these are transparent images. Mostly the transparent images are used in logos or vector cartoons and stuff like that. So this is how you can see, and all transparent images are PNG formatted, right? And like I said, each transparent image has an alpha channel. All right, so this way when you see images on Google, you know that if an image has a transparent channel or not. So check out this. So right now just downloaded this image of Google and also the transparent image. So this is the normal image without the transparent channel. You can already see the image starts from here and goes to here, and you can see all the background and the actual image in it, right? But when I open the transparent version, this one, you see that image is taking the background of this displayer. So this application's background, which is I think lightish blue or something like that, I'm not that good with colors, but it's taking up the background, and the only visible parts of the image are the logo itself. So this is a transparent image, and to load this image properly in OpenCV, you would need to put that -1 in when loading it up. Now let me show you how you would display actual images in OpenCV. So for that you would use this function cv2.imshow, and then you will enter the name of the image window, and then you will enter the actual image that you want to display. Alright, so this is not exactly important right now. You can give it any name. For example, I'm gonna give it image, and I'm just gonna add it even like window here. So image window, alright, and then I'm gonna put this image inside this window, and I'm gonna call this function, and this will launch the image window from which you can see the actual image that's being read here. So for this particular example, I'm using a different image, and I'm also reading it in color mode. Alright, so after using the imshow function, there's one other thing that you need to do, is that you need to call the wait key function. So this is the cv2.waitKey function, and in it you pass the number of milliseconds that the program needs to wait before moving on to the next line. And by passing it 0, it means that the image stays up indefinitely until the user presses the key. Alright, when the user presses any key on the keyboard, then the program moves on to the next line. And in the next line, I'm destroying the image window, which will just destroy the window, and the window will disappear and the program will end. Alright, so these 3 lines are normally used together whenever you're displaying an image window. Alright, so I could also comment out this line, and I could still be fine with these two, but the window would stay up. And this would cause problems when you're running the next line of code, because the window is up from the previous line and it's not going away unless you run this line and destroy the window. So let me just run this function right now, then I'll then get more into the variables here. Alright, when I run this, I'm gonna get this window. Alright, so this is the image, this guy that I've used, and this is the image window which I've just given the name here, image window. So that's the name that goes here, and this is the image which was read here and it's being showed here. So any key that I press right on the keyboard, it's gonna make this window disappear. Alright, so I could do this automatically. For example, if I put in here 500, alright, so that means that I think it's 0.5 seconds and 5 seconds. Let me just do this like 3. I think this is 3000 milliseconds, which is like 3 seconds, and it would make the image window disappear automatically after 3 seconds of launch. Alright, so this is me, 1, 2, and 3, I guess, yeah. So that's how this wait key function works. Either you manually, get rid of the image by pressing any key, or you set a timer for it. So normally when we're using images, it to display images, we put the number 0 because we want the user to be responsible for getting rid of the image. But when we're using displaying images in a video, in a real-time video feed, then we normally put in a number like 1 or 10 milliseconds or something like that. So this way, because the image is being displayed in a loop when we using a video feed. I'm going to get into that part later on, but I'm just telling you that when we're using a video feed, we put in a manual number like 1 or 2 or something like that, and when we doing images, we just put in 0, so that image stays up indefinitely. Now if I comment out this line, alright, if I comment out this line and then I launch this, and if I press on any key, see, it's just going to display me this number 1115, which is the ASCII code of the button that I've just pressed on. Alright, but see this image window not responding, and anything I do, it's going to the window is hanged up right now. So this is what I mean, it's going to cause you trouble if you don't destroy the window. So you need to run this line to get rid of that window, otherwise you won't be able to launch any future windows unless you get rid of this window. So let me just see this, and when I'm gonna run this line, the window disappears from here. So right now the window is gone, and if I run this again, alright, again, and the window launches it. Alright, so this is how this works. And I've gone and maybe discussed a couple of more details in the blog post version about the wait key function and the destroy windows function. I think it's above there, right? So yeah, so here I'm discussing when you press the escape key. Normally when you're using videos, we set it such that when we only press the escape key, the window closes. So the escape key's ASCII value is 27. So we put forth an if condition. So if the wait key returns an ASCII value of 27, which means the user has pressed the escape key button. So only then, break the loop and come out of the video. So I'll get into that when we're, working on the videos and stuff. So this is how we display images with OpenCV. Other than displaying images, we can also check the image properties. For example, I'm going to read this image and then I'm going to print out the data type of the image. img.datatype is going to tell me what data type the image is. And then I'm also going to do img.endIm, which is going to tell me what the number of dimensions of this image are. So when I run this, I'm going to get unsigned date. So unsigned date is what you're going to get when you're reading images with ImRead. So when you read images in ImRead, all the image channels are ranged from 0 to 255, and that's unsigned 8-bit integers, right? 0 to 255. So that's why you're going to get unsigned date data type. And because I'm reading a color image, I'm going to get 3 channels. If I do it like 0, I'm going to get 2 channels. And if I do it -1, I'm still going to get 3 because the image itself is not a transparent image. It does not have an alpha channel and it's still being loaded as a color image. Alright. So this is how this works. And let's now move on how we can access pixel values of an image. So let me give you an example of this. Let's see how we can access any pixel values in the image. So for example, take a look at this image. So this image, as we know, is an image matrix consisting of pixel values, right? So for any location that I pick up here is the pixel value on this image. So what would be the pixel value like for in the eyes of this guy? What is the pixel value in the hair? I know it would probably be 0 because the eyeball is black here. But what would be the pixel value here or any other random point that I can come up with? How would I know for an XY location in this image what's the pixel value here? What's the red, green, blue color channel value here, right? So this is how we would find out. So I'm saying for location X300 and Y300, what's the pixel value? When I print this out, I'm going to get this. The blue channel is 143, the green channel is 161, and the red channel is 168. So this is how I know that at location 300 by 300, this is the pixel value of that image. And similarly, I can even modify the pixel value at a certain location. So right now, if I do image 300 by 300 equals to 0, it's gonna set that pixel value to 0. And when I print this again, it's giving me 0, 0, 0. I've actually modified that image and that pixel location. Now, if I display that image again, I'm not gonna see a change because it's just 1 pixel, and you can't just see a change in a single pixel when the image is that large. So what we need to do to see an actual change is we need to learn to modify or access ROI of image, the region of images. So ROI or region of image, it's like a patch of an image. So let me show you an example of this. So for example, for this pixel, for this image, if I want to modify this square area in this image and make it black, so what I would do is I would specify from this section to this section, make this black, or maybe give me this section. So after doing that, I would get something like this. So this is what I mean by modifying ROI, region of images. So this is a region which is a set of pixels, a square region. So from this X1 location, X1, Y1 to this X2, Y2 location, I'm going to modify this whole area. So this is what I mean by modifying and accessing ROI of image. And this is how we do it in code. So I'm going to make a copy of it, of the image, by doing img.copy. This is going to give me a copy, and I'm then going to modify this copy, not the original version. Alright, So what I'm gonna do is that I'm gonna put img here, and then brackets, then I'm gonna say 100 by 150 and 80 by 120. Now this 100 by 150 is the y range. So y1, y2. So what's the height range? And this is the x range, the width range. So from 100 to 150, I'm gonna modify this part, and then the x part I'm gonna talk about like 80 to 120, x1 to x2. So this is the part I'm gonna modify, and what I'm gonna put it equal to, I'm gonna put it equal to 0. So which is gonna make it black. Now I'm modifying all RGB channels to 0. Now I could put a tuple here, like I want the red channel to be 23, I want the blue channel to be 54, and I want the green channel to be something like that. And then I'm gonna run this, I'm gonna get this greenish something like that. Maybe let's just make it 230 so I'm gonna get a blue color like this. So like that, or just make all the patches here 0, or maybe just change, like 140 here, like make the patch different, or maybe like moved up the location bit, like y range, and string it up bit. So you can do various sorts of manipulations with this ROI functionality. So this way you can modify any patch of an image, right? And similarly you can access any patch of an image. So this is how we modify an image and access patches of image either in pixels or ROIs.
Alright, let's take a look at how you can resize images. So this is a simple image pre-processing operation which you would use most of the time when using OpenCV. So you would need to resize image in certain height or width, and so you would need to use this function cv2.resize. This is a simple function in which you just pass in the image and then pass in the height or width which you want to resize it to. So 300 by 300. So this is what, so you first pass in the width and then the height. All right. So 300 by 300, and when I run this code, it's gonna resize it like this. So 300 by 300. Now there's a problem with that. When I am resizing it like this, you can see obviously the aspect ratio of the original image is not preserved. It's being distorted and it's not a good look. So we should figure out a way to resize an image without distorting the aspect ratio of the image, and there is a way to do that. But before that, there's one other technique of resizing which I would like to tell you, is that you just can use a percentage resize. So this is how you do it. So resize cv2.resize, and it's the same function, but now you would pass in 00, and then you would pass in fx equals to some value and fy is equal to some value, and this is the percentage of which you transform the image to. So by 1.5 I mean the image would be transformed, the x-axis would be transformed by 150% and the y would be also transformed by 150%. So when I launch this image, the image would enlarge to like 150% of the original size. And now because I'm transforming both these variables to a certain percentage equally, the aspect ratio would be preserved. But and in the same way, I can resize the image by like just doing 0.5 and 0.5, and the image is now being resized to 50% of its original size. But what if I want to specify certain value for a certain dimension and I still want to keep the aspect ratio of the image? Now I'm going to show you a technique which you can use to resize a certain dimension of the image but still keep the original aspect ratio of the image. So this is the code for that, but the condition is that you only can resize a certain dimension of the image. Either you resize the height, or either you resize the width, and the second dimension would be calculated proportionally so that the aspect ratio of the original image is maintained. So right now what I am doing is resizing by keeping the width 300 and the height, the new height, is calculated accordingly. So what will happen now is that I'm gonna read the image, and then I'm gonna get the height and width of the original image. So when you do img.shape, the height is returned first, then the width, then the channels. But when you resize an image, you first specify the width and then the height. So keep in mind how this works. I also keep forgetting, so I have to look it up in the docs. So right now what I do is I get the height and width, and then I compute a ratio. for the new height. So taking into account that 300 pixels is the new width that I want. So this is the new width, which is 300 pixels I want, and I divide it by the old width, alright, which is the original width. And then I get the ratio of the modification. So now I multiply this ratio by the height, and then I get the new height. I'm obviously like converting this into integers because it would be in float, and to specify a new height you can't resize an image in float. You need an integer because there's no such thing as like 30.5x, because when you have a matrix each image has an integer value. So now I'm this way I get a new height, and then I pass the new height in this cv2.resize function, and the width is kept at 300, which is the new width that I want. So when I run this code, I'm gonna get the image which has a width of 300 and the aspect ratio is maintained. So the aspect ratio of the original image is maintained, so there are no distortions like it appeared previously. So this is how you can maintain an aspect ratio and still resize an image. There are three ways in which you can resize an image. This is the old-fashioned way. You just modify the height and width to any number you want. This is when you modify height and width to a certain percentage that you want, and this is when you want to keep an aspect ratio, preserve an aspect ratio of the original image and still modify a certain height or width. Now let's take a look at some geometric transformations that we can do with OpenCV. Now there are many transformations like translation, rotation, shear, and even perspective transformations. But for this tutorial, I'm just going to focus on translation and rotation, which are the two most commonly used ones. And the image resizing, which we've just covered above, is also called scaling, which is another geometric transformation. So this is what I'm talking about, image translation. I will read the image from here, then I will grab the rows and columns and channels. Then I will create this transformation matrix, this one. Now this matrix would define how the image would be translated. So the translation is just like moving image up and down or sideways. So let me just run this first, then you'll be better able to understand this. So see, this image was here right now, and I've just moved it to the top left corner of the screen of the image window. So this is how I've translated the image. So similarly, I can just move the image in any given direction in the window. And right now, the image is filling up with like black borders, but you can similarly apply a flag and just duplicate this content with the replaced with this background, or you can replicate. There are multiple border techniques that you can use so to fill up this black space. So I'll get into that later, but what you need to first understand is how you can control this matrix to translate the image. So let me just go to the blog post which I've created. So this is the transformation matrix which you use to control the translation, rotation, and any other given transformations. Alright, so this matrix consists of three variables, and the last two variables in each row controls the translation. So tx controls the translation in x direction, and the ty controls the translation in y direction respectively. So these are the only two variables that you need to change. Also, if I like change this to 120 to 320, it would move further in x direction, and similarly if I make it plus, it would move in the opposite y direction. So I need to close this window first. Alright, so this is how, by just controlling these two variables, you can control how the image is translated. So that was translation. Now let's move on to the rotation part. So let's just briefly recap this matrix. This is called the affine matrix. The last column which we've just seen controls the translation in the image. The initial two columns controls the rotation, the scale, and the shear. Right now I'm just going to show you how to control the rotation, but I'm not going to show you how to modify the parameters of this matrix to control the rotation, because that technique requires several steps, and I'm going to show you a much simpler way, and that is you use the function called cv2.getRotationMatrix2D. in which you just define the anchor from which you're going to rotate the image, which is most of the time it is the center of the image. So that's why I'm going to do the calls divide by 2 and the rows divide by 2, which is the anchor point from which you will rotate from the angle. So this is the center point, and most of the time you will be rotating from the center, and then this is the angle of which I need to rotate the image. So angle I'm going to rotate at 45 degrees, and this is an optional scale. If I want to resize the image while I'm doing the rotation. So I'm not gonna resize the image, so that's why I'm gonna pass in just one which doesn't scale the image. And after that, I'm gonna get a rotation matrix. Now this is the matrix. Let me just print it out first. Rotation matrix, and this is the matrix. Okay, so before I show you this image, so look at this. This is the same matrix that I've constructed above. So if I wanted to find out if I want to rotate an image by 45 degrees, what matrix would I need to construct? Then you would need to do some mathematical operations, and all those operations are done inside this function get rotation matrix 2D, which returns you this matrix. So all you need to do is just get this matrix, rotation matrix, and pass in here, just like you used in translation. So in translation, obviously the matrix was pretty simple. You just did 1 0 0 1 and you mess with tx and ty. But in rotation it gets a little bit complicated. So that's why we have a function for it, and all you need to do is get rotation matrix 2D, and you get the matrix, and then you pass in the matrix here, you pass in the columns and rows, and you get the rotated image, which I've just shown you here. So you can rotate it by any angle, positive or negative direction, any way you want it. One other thing that you might be concerned about is what are these black regions? I mean, when you translate an image or when you rotate an image, you're getting these black regions. Is there any way that you can, like replace these black spots with, like the reflected versions of these, or maybe fill it out with some other color or something like that? So there's a couple of ways that you can fill these borders up. So for that, let's look into the function called warp-affine, which we're using in the translation matrix and in the rotation. Both are using the warp-affine function because both of these are affine transformations. So when I look at warp-affine and I scroll down here, I'm going to see border mode. So border mode would give me something like these border types, and when I click here, I'm going to see the number of options available to me. So what you can do is choose a different type. So instead of using a fixed constant number, you can use the replicate method or the reflect method. These two are the most popular ones, and then there are some other ones which you can use if you want. So most of the time I'm like going to use constant, and sometimes I'm going to go with the replicate or reflect if I don't want any black borders appearing. So the replicate and reflect are the most ideal options that you can go ahead with. Alright, now let's learn how we can annotate an image. So a lot of time we need to annotate or draw on an image to provide information to the user. For example, let's take a look at this. So this is an object detection problem in which I have to draw a bounding box around the detected object and also label it with a text, what the class of the object is and what's the confidence, detected confidence. Right? So a lot of time we need to display or write information on the image. So sometimes we may need to draw just rectangles, or sometimes we just need to draw circles around it. So we need to learn how we can use OpenCV to draw lines, rectangles, circles, or write text on the image. So for that, we can use a series of simple functions in OpenCV which are used to draw things like that. So what you need to do is just, we're going to make a copy of the original image. Then we will use this function to draw a line. cv2.line, we pass in the image, and then we pass in the x1, y1 coordinates, and then the x2, y2 coordinates. So if you want to draw a line, you just need an x1, y1 position and the x2, y2 position, and the line will be drawn here. So, and then optionally, we can also pass in the color that we want to draw the line with. So I'm passing it like I want the blue channel to be 255 and the red channel to be 255. So this would be a mixture of a blue-green color and the red 0 here. It's BGR in OpenCV, right? And this is the line thickness, I think. And so yeah, I've covered the variables here, I think. for each line. So yeah, for line, so yeah, these are the things that you would need. So this is the color. As you can either pass in a scalar value, or you can pass in a tuple like this in case you want to specify some specific color. And then you have line thickness, how thick you want the line to be drawn, and then you have the line type. There are multiple types of line. One is a dotted line, and it's a straight line. There are several types. So, and I've also linked in my blog post, I've also linked it to the documentation. So if you click on here, you will go right to the OpenCV docs, which would further tell you about each of the variables. And if you click on the line types here, just like that, you will see all the possible line types available for you to draw an OpenCV. So for each function which I'm going to show you right now, I have covered their variables, and I also linked it to their relevant docs, so that you can check out each variable. And it's really simple. So for the line, you just need an x1, y1, and x2, y2, and voila, you got a line here from this point to this point. Similarly, you can draw it from any point to any other second point. So this is a line, and the same variables apply to almost the other functions. So for a circle, if you want to draw a circle, all you need is the center point and the radius. So how big the circle would be. So that's what this is. This is the center point, x1, y1, the center point of the circle, and the radius. If the circle is, I want the radius to be 100, the circle will be this big. And if I run this now, so this is the circle. I've made a circle around this face. And if I made it like 200, the circle would be twice as big. And the same variables, the thickness, the color, these are these variables. And when it comes to circles, you can also fill the circle up. So yeah, by removing this thickness parameter and replacing it with -1, you can fill up the circle like this. So if you want a completely filled circle, then you would do -1. Other than that, if you just want to define a thickness of the circle, 5, 20, or whatever, you would just specify a scalar value here. So this is how we draw a line and how we draw a circle. Now let's take a look at how we can draw a rectangle on the image. So for that, to draw a rectangle, you just need 2 points, an x1, y1 point from here, from the top left corner of the rectangle, and then the bottom right corner of the rectangle. So these are 2 points that you need to draw a rectangle, and these are the 2 points here, x1, y1 and x2, y2. And this is the color, the thickness, the same variables. So this is how you draw a rectangle. By the way, obviously, once you know how to draw a rectangle, you can obviously measure the points to draw a square. So to draw a square or rectangle, it's the same function. All right. So how do we put some text on the screen, on the image? So this is how you do it. You pass in, you use the function cv2.putText, and then you pass in the image. You pass in the exact text that you want to put up. You pass in the location, the point from where the text would originate, and then you tell it what sort of font you want to use. There are multiple fonts available. One is CV to Hershey Simplex. This is the most commonly used font, and then there's another one which I commonly use. It's called Hershey Complex. I don't know if I'm pronouncing this name right. Anyways, this is the I think one is the thickness and the other is the font size of the line. So this is that. If I just changed it to like maybe 10. So yeah, this is the thickness variable, and this is the font size, and this can be in float, but this is in integer. So don't forget that, otherwise it would give you an error. So this is how you put text on the screen. So there are other functions too, that how to make an ellipse, but I don't normally use those functions that much. So these 4 functions are the one that you're gonna be using most of the time, specifically this rectangle and this text put text function, which we're gonna be using almost in any other application. Now let's take a look at how we can crop an image. So for example, I have this big image of Naruto, and I just want to crop the face part of it. So how do we do that? If we go back to this image ROI, accessing and accessing pixel values and modifying pixel values, it's the same thing in reverse. I mean, here you are defining an ROI and equaling it to some variable to modify it. What we would just do is, instead of equating to some scalar value, we would just extract it like this. So this is the ROI of an image which I'm interested in cropping out. So this is what I'm gonna do. Face equals to img some area in y and then some area in x. So this is what I'm gonna define it. It's the same thing which you just did with when we were doing the ROI manipulation, right? So this way I'm gonna get a cropped region of an image space, and the original image would obviously remain the same because I'm extracting another region and putting it on in the variable called face. So when I do this, so I'm gonna get this cropped region of Naruto's face. So this is how you just crop an image, as simple as that. Let's take a look at image smoothing or image blurring. So image smoothing is used when the image you want to apply some algorithm to have some noise in it. So that's when you use image smoothing. Now the most popular function for that is CV2.Gaussian blur, which get rid of Gaussian noise, which is the most popular noise present in most of the images and most common noise. So this is the result that you will get when you apply a Gaussian blur with the values, with these values. So this is the 9 by 9 by 9 by 9 here. This is the kernel size. So I am having a squared kernel of 9 by 9, and this is the sigma values. So both these parameters would affect how the blurring would be performed. The bigger the kernel, the greater the blur effect you would see, and sigma value will also impact how the image blurred. So there's a good theory behind how Gaussian blurring works. And then there are other blurring techniques like the average blurring, which is not as much useful as Gaussian blurring. Then there is median blurring, which is more which is commonly used to remove noise like this salt and pepper noise. And then there's bilateral filtering, which blur the image, but it also preserves the edges, which is sometimes a useful feature. There are different techniques that you can use to blur or smooth out an image, and all of these have their own specialties. And I can in fact make a whole video on it, and I intend to do that. But right now I'm just gonna show you how Gaussian blurring is working. Again, itself, which kernel to use, which blurring technique to use, when to use, that's a whole separate topic of its own. Alright, so that was image smoothing and image blurring. Now let's take a look at grayscale conversion or color conversions in general. So in OpenCV, you have a number of color formats. The most common one that you're probably familiar with is the BGR color format or the RGB color format, and probably the grayscale color format, which I've shown you how you can load an image in color mode and in grayscale mode. Normally, when you talk about images, color images, you talk about RGB images. So when you use image processing libraries like Pillow or maybe the image preprocessing modules in other libraries like TensorFlow or PyTorch, you normally working with images in RGB, right? The red channel comes first, then the green channel, then the blue channel. This is how the image is represented in the disk when you're working with TensorFlow. But in OpenCV, when you load an image, you load in reverse, not in RGB but in BGR when you're loading in colored images, right? So if you're using OpenCV along with some other library like TensorFlow or PyTorch, then you need to convert between the RGB or BGR formats, and that's when you use this function CV2.convertColor. So what you would do then is pass the image, and then you would specify how you want to transform your image, how you want to convert the color space. So if I wanted to convert a BGR image to an RGB image, I would do convert color BGR to RGB. So right now I'm not interested in converting to RGB because I'm only working with OpenCV, but I am interested in converting an image that I load in color in BGR, and I want to convert it to grayscale, right? So how would I do that? So an easy way to do that is to use the color flag called CV2.color BGR to gray. So there are many other color flags which would allow you to convert from one color format to many others. Like the most commonly used ones which I use is HSV color format, the LUV color format, and the lab color format. And these are the most common ones, which when I'm doing different type of task that come up with. So you would learn, maybe I'll make a video on color conversions and color spaces, and I will show you which color format is most useful. So because you won't always be using the RGB color format, in which we have 3 different channels and the merger of that forms any possible color. So for this reason, there are many other color formats. So take a look at this table, in which we have a list of flags for the color conversions, and OpenCV can almost convert from any one color space to any other color space. So from lab to RGB to LGB. I don't know all these color formats. I'm not familiar with them all, but like I said, the LUV and the lab, and these are the ones that are like the most common ones. And yeah, so you can take a look at this chart. And the way I got in here was by first going to the CVTR color doc, and then from there I went to color conversions. So all the links would be included in the blog post. You can check out this doc from there. Alright, now let's take a look at image thresholding. In thresholding, what we normally do is take a grayscale image, and then we just do some binary thresholding. So we specify certain threshold and tell the algorithm that all the images having intensity above this threshold should be equal to white, and all the images less than this threshold, all the pixels less than this threshold should be black. So once I run this, I'm gonna get that name grayscale. I think I didn't run this one. Or maybe the grayscale. Yeah. So this is how I'm gonna convert this color image into grayscale. Now once it's converted, I can run this thresholding function. So see, here's what I'm getting now. So initially all these were color images. Let me show you the original version here. So this is how it originally looked. Then after the grayscale conversion, it looked like this. So it's necessary to do grayscale, to convert the image in grayscale before doing thresholding. So that's why I applied grayscale. Now I have this. So as you can see, all these shapes have different intensities. So for example, the shape with the most brightest pixels is this triangle, and the shape with the most like the darkest pixels is this star. I think it's the most dark. So once I set a certain threshold, the 220, all the pixels in that image above 220 should be equal to this number 255, and all the image below it should be 0. So that's how it works. This is what CV2.thresh_binary does. So what you need to do is use this function called CV2.threshold. You pass in the grayscale image, then you pass in some threshold, which threshold you want, whatever you choose. Then you pass in the value that it would be equal to after the pixel exceeds and pixel intensity exceeds this threshold. And then you pass in the type of threshold you want to. The most common one is the thresh binary. Alright, so again, when I run this again, I'm gonna get this. But if I had chosen a value like 120, then I would probably getting something like this. See? So here I am telling this algorithm that all the images above 120 should be white, and all the rest, like below it, would be 0. So that's why the triangle is the first one that's gone, because it contained the most brightest pixels. So let me give you another example, and this time I'm going to show you the document in OpenCV. So this doc and this image specifically, this snippet clearly outlines how thresholding works. So take a look at this image. This is the original image, and after someone applies a binary thresholding with a value of 127. So this is how this image looks. So on the left it's 0, and on the right it's 255, and in between it's different shades of gray. So it goes from 0 to 255 from left to right. And when you take the midpoint, 127, right? So all the pixels here would be 127, right? it's the midpoint. So now I apply threshold with the value of threshold being 127 and the final value being 255. And when I do the binary thresholding, then all the pixels below 127 would be equals to 0, which is black, and all the ranges pixels above it would be white. This is binary thresholding. There's the inverse of this, which is called binary inverse, which inverts what everything that binary thresholding does. And so the black pixels would be white and the white pixels would be black. This is how binary inverse thresholding works. And all you need to do to shift switch between these two is change the flag. Instead of using cv2.thresh_binary, you use cv2.thresh_binary inverse. Note the same function, I'm using the same function in all of these different types of thresholding techniques. The only thing that's being changed here is the flag, right? So the only thing changed is the flag. This is how binary works, this is how binary inverse work, and there's another version called the truncated thresholding, which what it does is that all the images, all the pixels above the defined threshold, which is 127, will be equal to white, which is 255, but all the images below, all the pixels below it would maintain their original values, which is, as you can see here, all this part is just replicated below, but all the pixels above 127 have been equal to white, have been converted to white, which is 255. And then there's the zero threshold, the inverse. I actually never used these two. I mean, these three are the most commonly used one. In fact, most of the time you would even need to use the truncated version. You would be fine with binary and binary inverse. Although there are two other techniques, powerful techniques called adaptive thresholding, and it has two flags: adaptive threshold mean C, Gaussian C. Both of these are powerful techniques. And then there's also thresholding. And I'm not going to cover these because this is a whole separate topic of its own, how these thresholding techniques work. The most common and the basic one is this normal cv2.threshold, which is this one, and all you need to do is change flags. But the other two techniques would require different function altogether: adaptive threshold, cv2.adaptive threshold, and this one is, this is also a threshold, but you would use the OTSU flag plus OTSU flag threshold binary. And it's an interesting way how this works. So there's that. So going back here, and so this was thresholding, and if I inverted the thresholding, which I did above, I would get these results, right? So this is the whole thing is inverted. Now let's take a look at how edge detection works in OpenCV. Now, OpenCV has a number of functions like the Sobel detector and the Laplacian edge detector, but the most popular and the most effective one is the canny edge detector. And how canny works, it's really interesting. I can't cover all the theory, but these are the 5 steps it involves. First, there is Gaussian blurring, noise reduction, and then you find the gradients, and then there's non-maximum suppression, and finally a really clever thresholding technique is applied called hysteresis thresholding, in which a 2-stage thresholding technique is used. So in fact, in my course I covered this in great detail, how the canny works, but right now I'm just going to show you the results of how the canny edge detection. So all you need to do is just cv2.canny, use cv.canny, pass in the image, and then there are 2 thresholds that you need to tune in order to get the right edge map. This is the lower threshold and this is the upper threshold. So you need to just tune this and figure out what threshold values work for you. So let me just run this. So this is what I'm gonna get. So I'm getting an edge map of the outline of all the shapes that I previously had, right? So this is how edge detection works. So the most favorite part of this tutorial is this contours. So contours are really interesting because I've actually made a number of applications using just contours, like the virtual pen or the invisibility cloak or the virtual drum and many others. So, and all I used primarily in those applications was clever manipulation of contours and some pre-processing techniques. So what are contours? So by definition, I'm just going to show you the doc and first going to show you what contours are there, then I'm going to explain to you in a little bit more detail. So this is a simple definition of contours. Contours can be explained simply as a curve joining all continuous points along the boundary having same color or intensity. So it's just like a curve. Let me just draw this up. Like, for example, if I do this, this is a contour, right? This is also a contour. Like, I don't even need to close shapes like this. This is also a contour. This would be specified as one contour. But if I do this, then that, then these are two contours, right? So this is a curve of same intensity or color, and all the points are joined in some shape or line or some structure. So like this is also, maybe this is a like this is one contour, maybe this would be two contours. This would be an outer contour and an inner contour inside that. So there's also that. Now moving back here, if I run this edge detection again, this map was getting, I was getting this. All these are contours. So for example, all these shapes would be an individual contour. So this is one contour, two contour, 3, 4, 5, and 6. Now, as you can see the circle here, it's giving me some line over here. So if this line was separated from the circle, this would be detected as a separate contour. But if it's joined by this circle, then this whole thing is one contour. So if I just run this, and what I've done here is draw an outline over each contour. And in the next line, I'm going to print out the total number of contours detected in the image above. So what I'm getting are the total shapes present in the image are 6. And if I run this function again, I'm going to count the shapes 1, 2, 3, 4, 5, 6. So as you can see, by using contours, I can count the number of objects or shapes present in the image. So contours are really powerful tool. I have not only counted the number of shapes, but I've also segmented the shapes. By drawing an outline, exactly I know where each and every contour is present, right? So let me now go over line by line how this contour detection works. So first of all, what you do is, like I'm gonna make a copy of the image, then I'm gonna do some prerequisite steps that are required before you detect a contour. First, you need to, like convert the image in grayscale. Then what you need to do is convert, like threshold the image, so that you have a binary map, black and white map. And then you send that binary map in that find contours function, cv2.find contours. This is the binary thresholded image, and this is the same image which I was getting here. So this is the image which I let me just correct this threshold, which I just previously modified. Okay, so this is the map. I think this is, sorry, this is inverted map. This must be an inverted, yeah, thresh binary, because in contours what ends up happening is that the black is the background and the white is considered as the foreground. So the contours must be brighter than the background. So this is, if I do this, then all these shapes would be detected. Like this is a contour 1, 2, 3, 4, 5, 6. And I think if I had, you can also pass the edge map to the contour, and you can also pass this map. So there are two ways that you can pass an image to a contour. You can either do this image, which right now I'm doing this. I'm passing the inverted this map to the contour find contours function. But I can also pass this edges map here. But I think there would be a problem, because the edges, as I've just shown you, there was a problem here. So like there was this outline, which I think would be detected as a separate contour. So if I do this and then print out the shapes, yeah, see, 8 contours. So somehow some shapes are broken. So I think this is detected as separate contour, and this then star. Here this line is broken, so this is detected as a separate contour. I can maybe fix this by tuning these thresholds and getting the edge map right, but I don't need to do that because I've already got a solid technique. I can just use the inverted thresholding technique and get this map and pass this in the contour function and get my contours. So in practice, I normally either use the thresholding technique or the edges technique or any other segmentation technique you can use to get the contours map. All you need is a black and white image. Either it's an edges map or it's a thresholded image. All you need is a black and white binary image to get the contours. So now there are several other parameters that you can fine tune contours. So this is the black and white map for the image, and then this is the contour retrieval mode. Though there are several options, I'm not going to go over all of them. In fact, I think the contours in OpenCV are so extensive that in fact someone can make a whole course out of it. So again, they're really powerful. So this is the contour retrieval mode. By specifying retrieval external, I mean give me all the outer contours. So if I didn't do that and I say I've said retrieve all, I don't know if this is a valid flag. No, this is not a valid flag. So this is not a valid flag, but there are some options. If I go here and if I go to the contours function in OpenCV and then search for probably RETR, and I'm gonna get a number of options here. Okay, so these, yeah, here is it. These are the retrieval modes. So this is retrieval external, retrieval list, retrieval connected components, tree, flood fill. Though there are a number of techniques, these whole things are separate algorithms. So connected components is a separate algorithm, and the list will give you all the detected contours, so the all external and the inner contours. You don't want that. Most of the time you would be fine with external. Again, like I'm saying, contours itself is a really vast concept, and if you know how to use contours OpenCV to the fullest, believe me, you can create a number of exciting applications with it. Maybe sometime I will cover different topics in contour in detail. I plan to do that if there is enough all right, so right now I'm just gonna stick with the external mode. This is the one which I'm using. Okay, so now then there is a method, the mode, which I'm using cv2.chain approx none, which doesn't approximate and give me all the points. And then there is another approximation mode. Then there is cv.chain approx none, which is the mode that specifies how the points are returned. Let me just run this first. And so here's the definition for this. If you pass cv.approx none, all the boundary points are stored, but actually do we need all the points? So it's just for being computationally efficient, these modes are you have these modes. You don't need to worry about these modes. These are not that relevant. So cv2.chain approx none, and then finally when we have contours, all we need to do is use another function called cv2.draw contours. Now you can draw these contours by using cv.circle and then getting the contours each xy contour point and plotting it. But why go to the trouble when you have a function for that, cv.draw contours, which takes an image, which takes in contours, and then you specify how you want to draw the contours. You specify the color that would be used to draw the contours and the thickness. So by -1 I mean draw all contours, but so if I do that, it would do this. But if I want to draw a specific contour like 0, the first contour that is detected, it would do that. And then if I tell him to draw the third contour, it would do that. So this way I can draw selectively or either draw all detected contours. And then there are other things that you can also draw the most, the biggest contour, the largest contour, or the contour that is to the leftmost side or the rightmost side. So there are various manipulations that you can do with contours. All right. The most common use case is that to detect how many objects are present in the image or where the locations of those objects are. What's the center point of those objects? Again, I can talk all day about contours. Now let's move on to morphological operations. So morphological operations, let me show you first the documentation. So this is the documentation for the morphological operations in OpenCV. The two most commonly used morphological operations are the erosion function and the dilation function. And then by using a combination of both of these, we have opening and closing, which just does erosion and dilation, and the closing does the vice versa. First it forms first the dilation followed by erosion, and like I said, opening is doing erosion first, then dilation. You don't need to worry about opening and closing because you just only need to understand how erosion works and how dilation works, what these are doing. And then there are other things like morphological gradient, which does something like this, and the top hat and the black hat. I don't find myself using these three functions that often. Almost I don't think I've ever used these three functions. All right, so what erosion is doing is it takes this image. If you have this original image, it would thin all white segments in the image. So it would make a kernel go over the image, and it would like thin out all the white points present in the image. How exactly it works in theory is a little time consuming to explain to you, but because like I said, all these topics, it's a crash course. I'm not going to go into depth how the kernel convolution works in erosion, but just get this: once you pass in do erosion on something like this, all the white parts gets thinner. And if something is too small, it would disappear ultimately. And this is dilation. So it does the inverse of what erosion does. It dilates the object, it enhances the white objects present in the image. And obviously you first need to pass in a binary image, black and white binary image, to effectively use erosion and dilation in an image. So how is this useful? So this is the most prominent use case of morphological operations, is to get rid of noise in the image. So a lot of time when you do some segmentation work or something, like apply a model and it gives you a mask, the mask is noisy and you need to get rid of noise. So that's when you use these morphological operations. So look at this. So if you had this image and you would have, and you had this noise, white dots present in all of it. So what you would do, you would first perform erosion. Erosion would get rid of all the white dots, but it would also thin out this image. And then you would perform dilation to get the original shape of the target object back. So this is how you use erosion followed by dilation to effectively get rid of the noise. Right? This is called getting rid of the white noise present in the image. Similarly, you can get rid of holes or like black noise present in the image by doing a dilation first, which would like get rid of fill out these black holes, and then you would do erosion so that the target object goes back to its original size. And both of these noises are actually present in real world segmentations that you do. So a lot of times you get a white noise, and the mask of the original object is sometimes it got holes in it and you need to fill out those. So these are really two of the most important post-processing functions that you would need to do in a lot of computer vision applications. So these are morphological operations. So let me show you the results. Here I've got this image. It's when I wrote this, it's got this. Let me show you the original versions first. So this was my original image. It was I got these spots in it, like this one. And once I did erosion, I got all the spots removed. And similarly, I had this image in dilation, and once I apply dilation, all the spots are removed, but the image gets thicker. So if I need to get the original image back, now I would do erosion, and I would get this image back with this shape, but the spots would be removed then. All right, so let me just show you this in code. This is that erosion and this is dilation, and all I need to do is just use cv2.erode image and pass in the kernel. And the kernel, the shape of the kernel is 7.7. The larger the kernel size, the greater the erosion effect of the erosion. And similarly, there's also another variable called iterations. So right now I'm telling it iterations equals to 2, setting it iteration equals to 2. What this does, it applies erosion 2 times on the image. If I do it 3 or 4 or 5, you would get a much, the legs disappear, the legs were thinner. So this is how erosion works, and the same way the dilation works, you just need to change cv2.dilate image, you pass in the kernel and the number of iterations. I'm performing dilations 3 times. So I increase the iteration, the effect of the dilation would go up. And similarly, if I increase the kernel size, the impact of the dilation would also go up. So, and this is how you just construct a kernel, np.1s 7x7. I could also just specify a matrix here and fill out with 7x7 sevens. Yeah, so this is how the kernel is constructed, and this is how erosion works, and this is how dilation works.
Now let me show you how you can use the webcam feed with OpenCV. So now, since I'm going to use the camera with OpenCV, I've just closed the camera window from the recorder. So what I'm going to do first is just show you the normal pre-processing feed, and then I'm going to apply some basic pre-processing here. So So let me briefly explain what's going on here. What you first need to do is use this function called cv2.video capture and pass in 0 or 1, 2, 3, whatever, most of the time 0 would be equal to your default webcam in your device. If you're using a laptop, then 0 would probably trigger your device. If you're using a USB web camera along with your default webcam in a laptop, then this number would be 1, 2, -1, something like that. So that's what you need to figure out first, then use that number here. And after doing that, the camera would be initialized with cap, right, this variable. Then what you need to do is use cap.read. And when you call this function, what this does is it reads a frame from the camera and stores it in this variable frame, and then it also stores the status of that frame here in this variable. And now if the camera didn't read that frame successfully, it would store this variable as false. And if it reads successfully, then this read variable would be true. So that's what I'm checking here. If not read, if the camera did not read successfully the frame, then break the loop. There's no point in showing the frame. But if that's not the case, that if the camera read the frame successfully, then show the frame. And then I'm just using checking the wait key function. If the person press the Q key, then break the loop. So remember what I told you in wait key. When I'm using wait key in a video, I'm gonna specify something like 1, 2, or 3 milliseconds, something like that. And I also told you sometimes, I make a condition, check if the wait key, if a user pressed a specified key. And most of the times I check if the user pressed the escape key. And also sometimes I also use the letter Q for quit, right? So if the user pressed the Q key, then break the loop. So what ORD function is doing, it's just giving me the ASCII value of the letter Q, so which is 113. And if the user presses the Q key, cv.wait key would return 113. And if that's true, then I want to break out of the loop. I want to close the camera, release. You need to do this. You need to release the camera and destroy the window, right? So let's run this up. I have no idea why this pop up, or maybe there's some, okay, again. That is weird. I think I know what's going on here. I'm displaying the image, not the frame. Okay. Alright, so that's done, and this is me, as you can see. And right now I'm not applying any pre-processing functions here. So this is just me, and the camera is making me appear here. I can do a bunch of things here. I can do something like, like this. Maybe frame dot something like clip. I think it was that. No, it was like, I think it was frame equals to cv2 dot clip, and then frame 1. I think it could work. Not, I don't know for sure. Let's see if this let's do 0. Oh yeah, it worked. So it flipped the frame from left to right to right to left. It's a mirror image, and I can also create an upright image, I think by 0. So yeah, so this is how you can flip the frames, and I can also convert. You can do almost any other pre-processing thing inside, and it would work probably. So that the grayscale version of me. So this is the grayscale version that you're seeing right now. So as you can see, you can do any other pre-processing technique in this loop, and the video would be you would see the live feed. And you can also record by using the video writer function. There is another function called video writer. I'm not going to go into that. There's a lot of things that you can do, and you can save it to show it someone later, and for maybe later pre-processing and stuff like that. All right. So let me briefly go over some important variables in this video writer, this function, video capture function. So there are actually 4 things that you can do. You can view a live camera feed, which I was doing right now. Other than that, one other thing that you can do is play a video that is saved on your disk. So maybe I have something called smiling.mp4 in which I am smiling, and so I can play that video by passing the path to that video here. right? And then I can also actually stream live from the camera to OpenCV. In fact, I created an application where I did just that. So I built an application called Building a Smart Intruder Detection System with OpenCV and your phone. So this is a blog post which is published on my blog, in which I showed people how they can use their mobile camera and install an IP camera application here, and then you can live stream the camera feed from your phone to your PC and do some live computer vision, apply live pre-processing technique and computer vision techniques, and make a burglar detector, and also alert on Twilio on your phone. So it's a really nice and cool application, and the whole demos, you can see the whole demo on this 1-minute video. So it was something really cool, so that you can do here. You can use CV video capture as a live to stream live IP camera feed. All right, so that's the third thing that you can do. And the fourth thing that you can do is read a sequence of images. So if you have a sequence of images stored on your folder, or maybe another sequence of images that is you're probably commonly familiar with, it's GIF images. So if you have GIFs, then the best way to read GIFs is by using this function. You don't need to use immediate, because immediate would just read the first frame of the GIF, but what you need to use is CV video capture, which would read the whole GIF and display it. Right, so this is how you can read GIFs, stream live from an IP camera, or read video from your disk, or stream the live camera feed. And these are the variables that are returned. Red is most commonly used when you're reading from disk. So when you read the last frame of the video, then red would become false. So because there are no further frames left, if you're reading from a video and you have finally read the last frame of that video, it would give false, and that's when you automatically you configure this to break the loop. So there's two ways to that the loop would be broken. Either the red would become false, and it would become false when you're reading from a video which is saved on your disk, and it would become when you press Q, it would exit. So there are two ways to exit the loop. So this is how the live camera webcam feed works. Now let's talk about face detection. Face detection is one of the most common use cases in OpenCV. I've seen a lot of people using the OpenCV library just for face detection. And the reason they do that is because it's really easy. You can just do face detection in a couple of lines of code. So take a look at this. All you need to do is read an image, initialize a face detection classifier, and then just do face detection. That's it. You detect faces, and you have right now, by just doing these 2 lines of code, I have done face detection, and all I need to do is iterate from this returned variable and extract the faces, and then use the cv2.rectangle function to draw those coordinates. And I'm also putting up the text that the face is detected. So if I run this function, and let me show you the original image. So this was the original image. It doesn't have any faces. And if I go back here and show you the detected faces, so as you can see, all the faces are detected except this one, probably because the algorithm is racist, biased. I mean the alternative of I guess biasness, racism in algorithms is biasness, right? I don't know. So there's that. So almost all other faces are detected, and you can see the face written here, and the rectangles probably drawn here. Okay, so let me just explain this part. So what's happening here? So we're using a Har cascade classifier, and Har cascade is a machine learning based classifier. How this works, let me just give you a brief example of how this works. We use a Har cascade model, and then we show it a number of face images and a number of non-face images. These are called positive samples, and these are called negative samples. We show this to the model trains on it, and then what ends up happening is that the model learns to recognize faces. And what in Har cascades, what happens is that a kernel goes over the image. It finds some features which are called Har features, And what are exactly HAR features is like this. These features are something which you can refer to as HAR features, in which we have, like small edge detectors. This edge is responsible for detecting eyebrows. This is for like the right eye, and this is for the left eyebrow. This is responsible for detecting nose. As you can see, the eyebrow is probably dark, and the upper side of the eyebrow is lighter, so that's why we have a kernel that is like white above and dark below. And then the nose, when you look at the nose is brightest in the mid, right? And then the sides are a little darker, so that's why we have a feature, HAR feature, that detects if there's a nose present. And then we have a number of HAR features that randomly go over patches of the image and see if there are HAR features present. And if enough HAR features are present on some area, we call it a face. And then we do several iterations at several different scales of an image. So we use something called image pyramids, in which we resize an image by some ratio multiple times at different iterations. And then, because this way we can detect faces at different scales. If the face is bigger in the image, if the face is person is present far away in the image and the face is appearing really small, we can detect it too, right? So this way, by using image pyramids and a number of other techniques, we can effectively detect faces in the image. And this technique, in fact, is being used since I think 2001 or 2. And it's the most popular, it's also called the Wheeler-Jones classifier, and it was initially used to detect, when it was launched, it was a really big thing in the AI community. We were able to detect faces with great accuracy in the early 2000s, and it was a big deal. So this is how the face detection works. Again, it's a really interesting theory how HAR classifier works, and OpenCV documentation does outlines a number of processes that are involved, how we stack up weak classifiers, and then upon that we build up strong classifiers. And it's a really interesting theory. I'm not going to go over the full theory, but this is how briefly it works. So this was a brief description of how HAR features, or how HAR classifier works. Alright, so a couple of things which I would tell you. Number one, the HAR cascade or the HAR classifier is not just for the face. So it's a technique which is used to detect something. But the most common use case in OpenCV for that is the face detector. So I'm using this model called HAR Cascade Frontal Face Default.xml. It's a machine learning model that can detect faces. It's a HAR Cascade based machine learning model. And similarly, there are other models in the OpenCV repo. I would probably link this link in the description too. So I think this link is already present in the blog post. Probably I put it here, I think somewhere. Yeah, I think it's probably here present. So by the way, just a random note, I've also published a library called Bleed Face Detector almost more than a year ago, in which I've actually combined 4 different face detectors in this library. So by just using Bleed Face Detector, you can use 4 different type of face detectors in a single library, but you would need to install DLib first and OpenCV first. Alright, back to the second point. The first one is that you can use a number of other models. So this is the eye detector, this is the frontal face detector. There's also a full body detector, left eye detector, and there's also cat detector and smile detector, upper body. I mean, there are a bunch of other models. But to be honest, I've checked out a couple of these models and they are not that effective. The only model that works best here is the face detector, which is why it's the most commonly used, and it's also the most practical. The face detection has a lot of applications. Alright, so back to here, the second thing which I wanted to discuss was these 2 variables, this 1.3 and this 5. So the 5 is the minimum neighbor. So as I said before, that your image goes to several iterations, and if a face is present, it's actually detected multiple times, and the more times it's detected, the stronger the possibility is that it's an actual face. So if you're getting a bunch of false positives, if you're getting face detected on places that there isn't a face, so you would need increase this number. And similarly, if you're not getting a face where it should be one, then you would decrease this number. So this is a way to control the false positive detection rate of the face. And the higher the number is, the more confident the model is that this is a face. But again, if the number is too high, then even if the face is clearly visible, it won't be, you know, like listed out as a final detection. And then there is 1.3, this number. This is the image parameter ratio, how the image is scaled. So again, this number controls the speed of the classifier and also the, you know, like it controls the speed and the detection rate. So you can play around with these two variables. I've also briefly listed out the scale factor parameter specifying how much the image size is reduced at each parameter scale. So if this factor this factor controls the image parameter. So these two variables are something that we need to play around with. 1.35 works best for face detection. In most cases, probably it would work for you.
We have looked at how machine learning based face detection works. Now let's take a look at deep learning in OpenCV. So in OpenCV is not the ideal library to train neural networks, but it's the ideal library to deploy trained neural networks. Suppose you trained a neural network in TensorFlow or PyTorch, now you want to deploy it, you can use OpenCV for that. And OpenCV, you have a certain module called the DNN module. And the DNN module is used to, you know, like run a variety of deep learning models. So here's a brief pipeline that shows you how you can use a simple image classification model in deep learning. Alright, so this is how it would work. Let me show you here. So if I have an image like this, the first thing that I need to do is do something called pre-processing. So I would have an image pre-processing algorithm or techniques, some image processing techniques, and then I would have this image, you know, like pre-processed to certain size and may do some other pre-processing operations. And after that, I would, you know, like feed this pre-processed image in a deep neural network model. After that, I would get a bunch of, you know, like numbers or results, and then I would need to post-process these results to get a final label or a confidence along with that label. So I would need to do some post-processing, and after that I would get the final class label of that image. So this is how this pipeline works, and this is for just a simple classification, and along with classification you can do a number of other things. So now let's take a look at this whole process in code. So the first thing I will do is read this synset words.txt file in this variable and split it into, you know, like lines. So these are all the class names of the data set that this model was trained on. It was trained on the ImageNet, and it can classify 1000 in between 1000 classes. So let me just run this first, and then I'm gonna print the number of classes. So as you can see, the number of classes is 1000. It's just counting the number of rows because I've split each class into a singular row and, you know, like just cleaned it up. And after that, I would print out row 0 to 5 so that you can look at how this looks like. So as you can see, we have some ID number and then a name for the class and then some alternative names. So for example, for goldfish, I have this ID number and the name goldfish, and it's you know, like alternative names for each individual class. So for example, for a white shark, I have like white shark, great white shark, man-eater, man-eating shark. So like these are the alternative names that I've been given. So there's some car code, and I can't even pronounce this one. So as you can see from these results, in between each, you know, like column, there's a singular class. So I have 5 different classes represented here. Now what I would do is extract you know, like the first label after the ID. So this is how I'm going to do that. I'm going to run this line, and after that I'm going to print out the first 50 pre-processed class names. So from 10 all the way to crocodile, African crocodile. So I've got 50 class names here. So all I did was just, you know, like load up the class names in a text file and then clean it up a bit and then extract singular class names. So now I have a Python list of 1000 length, and in each item is a class name. So now all I need to do is you know, like load up my deep learning model. For that, I would use this function cv2.dnn.readNet from cafe. Now this deep learning model was trained on cafe. If it was trained on TensorFlow, then I would be using readNet from TensorFlow. If it was trained on PyTorch, then there's another function for that on Torch, and if it was Onyx format, then there's another function for that, and there is another global function that reads a model in any format. So I'm not gonna go into all details, but for what it's worth, I've covered a number of details in this blog post that you can look up. Yeah, you can follow along with this post, in which I think I have mentioned a number of things here. Anyways, back to the code. So what I'm doing is specifying the two different variables here, architecture and weights. So these are the two files that you would need to initialize the model. The first one is the weights. These are the weights of the neurons in that neural network. So these are the actual trained weights that the model will use to predict, classify the image. And then this is the architecture. This is how the model is structured, the structural information about the model, its architecture. So this is that file, so .proto.txt. So these two files are required when you're initializing a model: the architecture of the model, how the model looks like, how it's designed, and the weights that have learned upon training upon that data set. So these two files are required. Now I would run this, the model would be initialized, and now I'm gonna do pre-processing in this step. So what I'm doing is reading an image like this. I'm gonna read the image, and then I'm gonna convert that image into a blob. The blob is, you can think of blob as a pre-processed version of that image. So there's a function DNN module called cv2.dnn.blob from image. What it does, it pre-processes an image. It does a number of things. So it takes an image, it can multiply by some number, and it would normalize it. So normally, if I want to divide all pixels by 255, which is a common normalization technique, then I would just do do something like that, and this would convert all the images in the range of 0 to 1, which is a common normalization technique, but I'm not doing that. The other thing that we do is resize an image to a fixed size. So one of the most common sizes is 224 by 224, and this is the same size that different models that trained on ImageNet use. So it's the size that we need, 224 by 224. The width and height would be resized to this size. And then we are also doing is we are doing some mean subtraction. So mean RGB subtraction. So these are the RGB or BGR values that would be subtracted from that image. So this is another pre-processing technique that the authors of the models use, and we're also using it here. So if I run this, and then I'm gonna print out the blob, as you can. Okay, I'm gonna print out the shape because. Alright, as you can see, it has added another dimension to it, an extra dimension, because normally we work in batches, so that's why you need another dimension here. That's the channels, and then the image is resized to 224 by 224. So our image has been pre-processed, and all we need to do is set it to the network and run a forward pass to the network. So all I will do is net.set input blob. So I've initialized the model here, and I'm passing the pre-processed image to the model, and in the next step I'm gonna run a forward pass. This is where all the computation happens. Once the network has been trained, all you need to do is take an image and forward pass it through the network, and what comes outwards is the predictions. So once I run this, I've got something called the output. Now this is the results, this is the predictions. All I need to do is just post-process it. Since it's just a classifier, there's not much post-processing happening. All I need to do is grab the most confident prediction, extract index, and then use that index to get the label name of that class. So I'm gonna print it out. So the total number of predictions are 1000. As you can see, the output, the length of that vector that is has been returned to me is 1000, as it should be, because we had trained the model with 1000 classes. Output vector length should be 1000. Now what I would do is just print out first 50 outputs, so you can see from yourself what these what does the output look like. So this is what I am having. These are the probabilities for each class. So 1000 that the vector of length 1000 that has been returned to me is the probabilities for each class. Now what I would do, it get the maximum probability. So for example, I have a probability for each class. So the model thinks that model predicts some probability for each class. But because the image I'm using is the goldfish, so the highest probability for a well-trained model which I'm using would be the goldfish, because the image was goldfish, and if the model detected it correctly, the highest probable class would be the goldfish. Now I can check this out by getting the maximum probability, and it's telling me the class with the maximum probability is 99% sure. So it's sure that this class, it's the actual class by 99%. So it's really sure, and the index of that class is 1, and which equates to 0, 1, 2, right? It's the second class. And if I look at here, tench 0, 1, this is the class which this index is pointing to. And if I use this list and this index to grab the item in this list, I would get the number, the index, the text goldfish. And this is what I would get by doing print classes index the goldfish. So this is how image classification is done with the DNN module. Just for the sake, I would draw a goldfish on the image and just show it to you with the imshow function. So this is how the final result looks like. I've got the label goldfish and its confidence 99.85% sure, and the actual image itself. So that's our whole pipeline for the DNN module. Since this was a classification, the post-processing was really simple. But when you use things like detection, segmentation, and key point estimation, then you need to do several steps in post-processing and also in pre-processing. Fortunately, in pre-processing, you can just utilize this function, cv.plot from image, and most of the time you would be fine with using just this function. Sometimes when you're using some different models that are not officially supported in OpenCV, I did that once when I used super resolution. So I took a different model that was not supported in OpenCV, and I tuned and came out with a different pre-processing scheme, but didn't utilize block from image because it didn't supported it, but it still worked out at the end. But I had to do a couple of custom things to get this working. So I have also published that blog in OpenCV and on that super resolution post, and I have also I also have this series, the deep learning with OpenCV DNN module comprehensive guide. This is the most comprehensive series on DNN module in OpenCV that you will find on the internet. So this is a 3-part series: deep learning with OpenCV DNN module comprehensive guide, then training a custom image classifier with TensorFlow converting to ONNX and using it in OpenCV DNN module, and then using a custom trained object detector with OpenCV DNN module. So this is a 3-part series, and it's a really great series if you're interested in using deep learning with OpenCV. Again, if you're primarily interested in training neural networks, then OpenCV is not the library that you need to use. You need to use TensorFlow and PyTorch. For deploying, OpenCV is a great choice, and there's still a couple of problems after especially after TensorFlow came up with the second version, because there are a couple of converting problems, but once those issues are resolved, OpenCV is a great choice for using pre-trained models from TensorFlow and PyTorch. Alright, so I would strongly recommend for you to go through these series if you're interested in getting the most out of the DNN module in OpenCV. In fact, in my course in Bleed AI, the Urdu Hindi course, I went over a number of things: age detection, image segmentation, object detection, SSD object detection, classification, gender detection, facial expression detection, image classification, super resolution with DNN, neural style transfer. So all these things can be done with the DNN module, and I have actually showed you how you can do all that with the DNN module. So I have separate videos for each of these topics in that course. All these topics are briefly covered, but you do get to see the code and how it works. So there's that. Alright, so this was the final pipeline for image classification. So that was a full crash course on OpenCV, and to be honest, this was the first time that I ever did a tutorial, a non-scripted tutorial in English. So I've done a lot of tutorials in my course, but all of those were in Urdu Hindi language, and this is the first time that I've done a non-scripted one in English. So please do let me know if you found this tutorial useful, and I apologize for any mispronounced words or any things that were miscommunicated. So So and please do let me know. It's really important that if people find this tutorial of mine useful, so this tells me if I can keep making on like tutorials like that, and if you're finding these useful or not. So if you sticked around till the end, then do let me know in the comments if you found this stuff useful. The episodes of CV for Everyone will keep on coming, but like I'm also planning to put out videos like this every week. So and I've got a lot of stuff that I can teach, and this non-scripted techniques allows me to push out videos faster, much faster. So if this is helpful for you, do let me know. If you have any questions, put it in the comments. I promise I would answer each and every questions in the comments properly. So yeah, and thanks for watching. Bye.